So glad you stopped by. So anyway, as I was saying, Robert, Robbie, Bobby, Bob. Let's go with that. Try to make these videos somewhat entertaining, for the students. Really do, while at the same time trying to get information in there they need in order to learn the math and be able to do the assignments.
Oh, that's really cool. I appreciate the kind of complexity of it.
So back when you were in high school, you were a big fan of math and math class, right?
Sure.
Yeah, that's cool, man. I was talking with our principal, Dr. Guthrie, this week. You did know that he graduated this month with his doctorate, right?
Yeah, he's becoming a better guy.
Yeah, we were talking about, we've got all these lessons out there, all these great lessons. And, some students are they're skipping the videos and just going straight to the assignments and trying to do the assignments without ever learning the lesson. That wasn't you in school, right? You were one of the ones that paid attention to the lesson, right?
Sure.
Yeah, some of the students, they're really sharp in math, and they don't have a lot of problem doing that. If there's something they don't understand, they look it up on the internet, and they seem to do okay. But there's a lot of these students that, man, they have no idea what's going on. You can tell by what they make no sense with the answers they put on there. They really need to be watching the video.
Are we promoting a movie?
Oh, sorry. Where was I?
Your foot's starting to jump a little bit. You better get to your next question.
Right. So we're just about to wrap up the school year, and
What are we doing?
oh man, it's late. I got to do a lesson. I got students waiting on me. I'm sorry. I got to run.
Bye.
Oh, cue my intro. Hey, I'm coming. Hold. Sorry. Got a little distracted. All right. Oh, hey. All right. You're here. Boom. There we go. All right. Hey, yeah, I got a little preoccupied, lost track of time, but good to see you. Wow. Last week of school for the year. Then officially summer coming. So we got today's lesson. Short. I just want to show you some cool stuff. Wednesday we'll have something kind of fun. So watch the video. Just have something for you to do then. And then there's the Thursday, Friday, next Tuesday was supposed to be finals. Not going to be finals. So you should have an email by now from the school detailing it's a competition between us and those other guys over there at that other high school. So look through there, find some good stuff. Let's rack it up. Let's get a win for West, right? Win for West, baby. So, all right, where were we? Oh, today I wanted to show you. I got to thinking, all year round we got into trig functions, right? We were doing sine and cosine. We kept saying, check your calculator. Make sure your calculator is in degrees, not radians. Degrees, not radians. So I thought, let's end the year telling you what a radian is. You know what degrees are. We've talked about degrees for a long time. So today we're going to look at radians just briefly. And let me switch over there. Okay. A new way to measure angles. Okay. Just make sure we're all focused in. Grab me a pencil. All right. A new way to measure angles. So a 1 unit radius. Okay. This is a unit circle. When you hear the phrase a unit circle, that's one specific circle. It's a circle that has a radius of 1 unit. It could be 1 centimeter, 1 inch, whatever, but it's 1. It's a unit, 1 unit. So a unit circle has a radius of 1. Remember that. There's a question on today's assignment. Unit circle, that means it has a radius of 1. You don't have to say anything except it's a unit circle and you know how big it is. So this is a unit circle. This one I have written the radius on there, right? We have the radius of 1, so we know it goes from the center origin, it goes to 1, 0. The highest point is 0, 1. Negative 1, 0, and 0, negative 1 would be the edges of our circle up and down and left and right. So if a circle has a radius of 1 unit, which this one does, it's a unit circle, find the length of the arc. So we're looking at the length of the arc defined by each of these central angles, and give our answers in terms of pi. So the length of the arc would be a portion, how long is that around there of the circumference. So what about the entire circumference of a unit circle? Now remember, circumference equals 2 times the radius times pi. Or it equals the diameter times pi if you have the diameter, but we have the radius. So 2 radius is the same as 1 diameter, right? 2 times the radius. Well, our radius is 1. So this circle has a circumference of 2 pi. Right? 2 pi. That is all the way around the circle. So if we have 180 degrees, an arc defined by the central angle, it's 180 degrees. So let's say it starts right here. And our central angle, the angle right here, goes 180 degrees. So we're talking about that arc right there. How long is that arc? Well, 180 degrees is 1/2 of 360, right? That's 1/2. It's the same as 1/2. So we would have half of the circumference. And since the circumference is 2 pi, halfway around would just be pi, 1 pi. 3.14159, that continues on. So it's a little over 3. It's a little over 3. It's the length of pi would be the length of that arc. How about 45 degrees? Where would 45 degrees be? Well, this is 90 degrees. 45 degrees would be half of that. Half of that. So if we look at that, there's 4 of those. 1, 2, 3, 4 in half a circle, right? 45, 90, 135, 180. There's 4 of those equal ones. So 45 would be 1/4 of the one we just figured, pi. So 45 would be pi divided by 4. We could have also done it with the 360. 45 out of 360 is what percentage? It's 1/8. So 1/8 times 2 pi would be 1/4 pi, or pi divided by 4. So 270 degrees. Okay, so we know this is 90, this is 180, this is 270. So if our arc, our central angle came all the way down to here, and we want to know the distance of that arc, it's not 2 pi, because 2 pi would be all the way around. It's not 1 pi. It's halfway between 1 and 2 pi. So what's halfway between 1 pi and 2 pi? It's 1.5 pi, but we don't write 1.5 pi. We would write that as a fraction, an improper fraction. 3 pi over 2. 3 over 2, that's 1.5, right? 3 halves is 1 and 1/2. 3 halves. So it's 3 pi over 2. That's the same thing as writing 3 halves pi. But you generally don't see 3 halves pi. You see 3 pi over 2, because this pi is actually over 1. And so since it's the numerator, we put it with the 3, and it's 3 pi over 2. So 3 halves, because this is a pi, this is half a pi, this is a pi plus a half a pi. So 1 pi plus a half a pi. Pi plus 1/2 a pi. See, 1 pi would be the same as 2 over 2 pi. So 2 over 2 plus 1 over 2 is 3 over 2 pi. All right, 360 degrees. The arc defined by the entire circle is going to be equal to the circumference, 2 pi. 2 pi. And you're like, okay, what's this have to do with the radians? You said we were going to talk about radians. These units are in radians. What? Yes, this is radians. When we say, how long is that? We say, well, it's 90 degrees. Or we could say that is pi divided by 2. Radians. Distance in radians. Okay, let me look at that. So defining radians. All right, suppose we have a circle that has a central angle, and the radian measure, the measure in radians, not degrees, is the angle of the ratio of the length of the arc defined by the angle of the circle's radius. What? The arc length divided by the radius. Okay, now you're throwing a whole bunch of vocabulary at me, and it sounds really confusing. I have something to show you. Let me switch over here. Let's look at this. This is going to be a lot easier to understand. Okay, we have a unit circle. All right, this is a radius of 1. It doesn't have to be. This could be a radius of 10, but we're just going to call it a unit circle. Whatever this unit is, whatever the radius is, it's this blue line. Now, suppose we're starting to look at an arc. We're going to take this arc and we're going to take this blue line and we're going to move it and say how far does that wrap around the circle? How far does the radius wrap around? So I'm going to grab this and we're going to move it. See the blue line moving? The blue line's moving till right there. Okay, so this blue line is the same as the red line. We just took it and we pulled it out and wrapped it up around the circle. So since this distance is equal to this distance, the ratio of the arc to the radius is a 1-to-1 ratio. That distance is 1 radian. Right here, this arc, this blue is 1 radian. 1 radian. Let's say we can take that out farther. 2 radians. See, now we have the blue and the red on the arc, and the green has replaced it, another one. That's 2 radians. Let's go 3 radians. 3 radians. See how far 3 radians is? So that's a distance of 3 for the arc. And we said that half of the circle is how far? It's pi. What is pi as a number, a decimal? I know it continues. We'd have to round it. 3.14159. Just a little over 3.14. That's why 3 radians is just a little bit short of halfway, because all the way to 180 degrees, taking it right down to there, that's 3.14159 radians. It's just a little over 3. See, we got a little bit of the yellow added on there. So this truly is like the number 1, the number 2, the number 3, if there is a radius of 1. If there's a radius of 2, we've got to multiply it by 2. If it's a radius of 5, we've got to multiply, so it would be bigger if the circle was bigger. But if we just say this is a radius of 1, then that radian is going to be equal, each radian is equal to 1, because that's our radius. So in a unit circle, each of those is a 1. But that is what a radian is. A radian is the relationship of the length of the arc compared to the radius. So 1 radian is a 1-to-1 ratio of the distance around the arc. So how far is it around the entire circle? How many radians will it be? Well, we said 2 pi, but pi is 3.1415. So if we double that, 2 of those, we're looking at 6.28 something. So we should have 6 radians and about 1/4 of another one. So let's take our arc and extend it around the circle. Okay, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians. Oh, look, we haven't quite made it to the circle. We take a little bit farther right there. That's about 1/4 of a radian. About 1/4. 6.283, right? So we're looking at 2 pi. So that, if that gives you an idea why you have to have it in degrees as opposed to radians, there's a big difference. All the way around the circle is a little over 6 in radians. Less than 6.3. Excuse me. So the difference in the 6.3, and how much is that if we have it in degrees? Well, that's 360 degrees. There's a big difference in radians and degrees. So that's why when we're doing all of that in a calculator, make sure your calculator is set in either radians or it's set in degrees, because there's a big difference in what your answer will be. So kind of leads to the thought of, where did we come up with 360 degrees? Radians, I can see, it's just a relationship. 1-to-1. When the arc size is equal to the radius, that's 1 radian. So we can understand that. But where did the 360 come from? How did we decide that a circle is 360 degrees? Well, if you research that, looking back at some math history, no one's exactly sure how that one started. We don't have like a person that discovered it's 360 degrees. But it most likely goes back to the ancient Babylonians. The Babylonians had a number system that was base 60. You're like, base 60, what do you mean? Well, our number system is base 10, right? 10 and 100 and everything. And the decimals is a tenth and 100th, and everything's based on tens, multiples of 10. That's our number system. Their number system was based on multiples of 60. Odd, right? Very, very different. But that was the Babylonian number system. So seeing that 360 is 60 times 6. So that is in the number system of the Babylonians. 360 degrees is just right along lines in one of their multiples of the 60 that they used. Also, you could tie it back and say it also kind of relates to the fact that if you had equilateral triangle, if we took 6 triangles and we put them together, like a pizza, right? If we took 6 equilateral triangles, it would make a circle, sort of. The edges would be straight for the triangles. But it completes the circle by having 6 equilateral triangles all the same size. And in an equilateral triangle, all the angles are the same. So all the angles are 60. So if we have 6 60-degree angles, that's 360. So there's lots of tie-ins to how we come up with 360. The Babylonians, they were responsible for a lot of what we still use. Our minutes and hours are back from that old ancient Babylonian system. We have 60 seconds in an hour. We have 60 seconds in a minute, 60 minutes in an hour. It all goes back to the ancient Babylonians. It's pretty cool to see where a lot of this came from. I love the math history and all this cool stuff. But anyway, that's what I wanted to show you today. That's what we're going to end up the year with. We're just showing you what a radian is. Drop those things there. Showing you what a radian is. I'll have, maybe 2 or 3 questions today. It's going to be real simple to wrap up the year. Like I said, Wednesday we'll try to have something kind of fun for you to do. Love to have a chance just to see what you're excited about for the summer, see what you've learned, and give you a chance to see what your classmates are doing, perhaps. So look for that on Wednesday. But otherwise, if I don't see you again, I do look forward to seeing perhaps Wednesday. But have a great summer and come see us next year. Should be like down the math wing, you know where I am. So let's finish it strong, guys. Let's get this done. All right. Do work you can be proud of. See you later.